like to get started. Good morning. My name is Joe Labuz, Department Head for Civil, Environmental, and Geoengineering. Welcome to the department's Warren Seminar Series, which is made possible by a generous gift from Alice Warren, and for this we are truly grateful. Today's seminar is special because we're here to honor the legacy of a very special person, and that is Yanis Vardoulakis, a former faculty member in this department. Yanis received his degrees in civil engineering from the National Technical University of Athens and then from the University of Karlsruhe. He joined the University of Minnesota in 1980 and rose to the rank of professor in 1987. Yanis was an international leader in geomechanics, and his contributions spanned many areas, among them experimental mechanics, constitutive modeling, granular flows and landslides, bifurcation theory, liquefaction, and computational mechanics. And we'll see Yanis's influence when we hear from today's speaker. And it indeed is my privilege to introduce the 2016 Vardoulakis Lecture, Professor Panos Papanastasiou from the University of Cyprus. Sorry, Panos.
That's right.
Panos is a faculty member in the Department of Civil and Environmental Engineering, and he served as Dean of Engineering from 2009 to 2014. He was also the founding head of the Department of Civil and Environmental Engineering from 2002 to 2008. He was or is also the founding director of the master's program in petroleum engineering at the University of Cyprus. Panos received his diploma in civil engineering from the National Technical University of Athens, and then his MS and PhD in 1986 and 1990 from civil engineering here at the University of Minnesota. And of course, he was one of Yanis's best students. Panos worked for about 15 years in the oil and gas industry at the prestigious research center of Schlumberger Research in Cambridge, England. He then joined academia at the University of Cyprus. His expertise and scientific contributions are in the area of computational mechanics and petroleum geomechanics, including problems on wellbore stability, hydraulic fracturing, sand prediction and control, and CO2 geologic storage. He's published over 100 scientific papers, 5 book chapters. He has 3 patents. He's on several editorial boards, including the International Journal of Geomechanics and Petroleum Science. Please join me in welcoming Panos.
Regarding my last name, Professor Desai say, if I can call you Papa, nice to see you, I will be quite close.
Should have told me that before.
Yeah.
And I practiced.
Anyway, thank you very much, Joe, and the department for this invitation to deliver the lecture in honor of Yanis Vardoulakis. It is very emotional for me to be back 26 years after I defended my PhD thesis in this room, and to give this lecture in the memory of my PhD advisor, Yanis Vardoulakis. I remember the years from 1985 to 1990. He treated me very well, especially very well. So I will always remember him and honor his memory. Now, I will talk about hydraulic fracturing. And just to acknowledge the organization that support my research and the people with whom I cooperate, and we wrote publications. And I will just mention here particularly Mark Tirselen, He was the guy that introduced me in hydraulic fracturing, and he died young in 2010. Mark was a great scientist, great engineer, innovator, and a great man as well. He was a French gentleman, and I will always remember him. He was the guy who introduced me to this area of hydraulic fracturing. Other people I worked with him was Emmanuel Dedournay when I started in Cambridge at that time. Jean Desroches is still with Schlumberger. I cooperated with Colin Atkinson, emeritus professor from Imperial College. At the University of Cyprus, my research was supported by the Cyprus Research Promotion Foundation. He provided funding for a PhD thesis of one of my students, and then as a postdoc. And I had also some smaller collaborations recently with Greece, with Euripides Papamikos, another student of Professor Vardoulakis, and a research project with Sindef Petroleum Norway, a smaller project. So basically, I will talk about hydraulic fracturing, but my research focuses in weak rocks, hydraulic fracturing in weak rocks. I will present the applications and the issues in this topic. Of course, it's the hydraulic fracture, it's a big issue in petroleum engineering to stimulate and decrease production flow in the reservoirs. And it is used also for rejection of cuttings in shallower formations, weaker formations. And it is used also in a new technology, frac packs is called, when we couple thinner reservoirs, we connect it with a fracture to avoid sanding, not to produce sanding. Again, there is a fracturing there to do. And the issues, it's always we try to improve the models to predict the pressures correctly and the fracture dimensions, to look at also that the fracture will remain in the interval. And then recently with the evolution in shale reservoirs, there was a need to have a kind of an index which can be used to select the intervals where to carry out this hydraulic fracturing, and I will talk about that. And then other applications which are related to weak rocks we have in environmental engineering, geotechnical engineering, and more recently, I look at also another area, the CO2 geological storage, and it's a big subject, and there is a lot of research going on that area. And just to understand, to give you an idea about this problem, there are some suggestions by International Energy Association based in Paris about CCS. CO2 capture and storage must be part of the policy for mitigate climate change and to achieve the target of keeping the temperature 2 degrees, the increase in the temperature to be less than 2 degrees Celsius the next 50 years. So to achieve this target, we need to make a lot of investments, the international community. Most of the investment is in efficiency, in renewables. Nuclear, it's part, and it's connected with geomechanics through nuclear disposals, the waste. And you can see here also part of this policy should be the CO2 capture and storage. There are estimates that the international community should invest around 75 billion a year on this CCS project. Most of the technology on CCS exists in the oil industry. They develop most of the technology, but it is still expensive. And the economics work if it is combined with other technology like enhanced oil recovery, and I don't mean necessarily hydraulic fracturing. Outstanding issue is the risk of CO2 leakage, and the research community should answer this question for the policymakers to make the decisions and go to the investments. Now, if we look at the mechanism of CO2 escapes, A particular problem in the United States is the risk of escaping through existing abandoned wells due to the bad cementing. And there are 1,000 wells in areas which could be good basins for the CO2 storage. Escape of CO2 through non-sealing faults, through the diffusion through the cap rock, or through capillary leakage. If the ejected pressures exceed the capillary pressures in the cap. And my work will focus on the risk of inducing hydraulic fractures from the pressures generated by the CO2 injections. And when this pressure exceeds the closure stress. Closure stress is the in situ stress, the geostatic stress, against which the fracture is formed. The fracture is formed perpendicular to this closure stress. And I will add something here. Now, what I will try to make a story here, I'll try to show that a fracture, a vertical fracture, you can see a wellbore here, and the vertical fracture. And I will try to make a point that the fracture is more likely that it will propagate horizontally than vertically. If the fracture doesn't propagate vertically, then we reduce the risk of CO2 escape. On the other hand, if the fracture propagates horizontally, we resolve some issue with the CO2, like we can increase the wellbore ejectivity, which is a problem in CO2 injection, because due to the corrosive nature of the CO2, we have the dissolution of the salts and the blockage of permeability. So a fracture will increase this permeability and be able to increase also the storage capacity of the formation, which is another issue. And of course, to know where the fractures will go and have a good indication of the fracture geometry, we need to have good models. And to have a good model, we need to look at the mechanisms around the propagating fracture, and especially the area near the fracture tip. In this picture, I have a horizontal cross-section or a vertical wellbore. This is a vertical wellbore. This is just a horizontal cross-section with the fracture. The fracture is vertical as well. So this is the horizontal picture as we see it from the top. And to imagine the full fracture geometry, just rotate only the fracture 360 degrees around. You see the complete vertical fracture. So this fracture can grow in every direction, in the horizontal, to propagate horizontal or vertically. Now there was an issue with predicting the pressures which are needed to create this fracture. And the issue was that most of the model couldn't predict correctly the pressure that it needed to propagate the fractures and then the fracture dimension. Basically, the pressures in the pressures in the fracture was the only parameter we could measure. And when we were running the simulators and then going to the field to make the operation, we often find that the pressure needed in the field was much higher. And to explain the discrepancy, there was a lot of approaches, and I mentioned here also the work of Emmanuel Detourné and his students to get better modeling of the growing of hydraulic fracture. Here I look at again the wake rocks, and some of the suggestions were proposed to explain the discrepancy between models and field measurements. One was based on fluid lag, that the fracture fluid doesn't reach the actual tip. There is a lag near the tip, and since this area is very sensitive, we need much higher pressure to propagate the fracture. And then there was a suggestion that rock dilation even will enforce bigger fluid lag. And then another suggestion was saying that in the field we have high apparent fracture toughness due to different resource scale effect, confining pressure, heterogeneity, we may have scale effect. And also later I will show that it's in short fracture is very likely when we do calibration test in the field and we measure the pressure versus time, and then we invert the pressure versus times to determine some formation parameters like permeability or the closure stress. It's very likely using the elastic models to underestimate the closure stress. And if we underestimate the closure stress, the minimum stress, then we will need higher pressure in the field to propagate the fractures. In the work here, I tried to look at these different approaches, and I set up a hydraulic fracturing model, fully coupled, and then I say that I'm focusing in my work in weak rocks. And if we try to do hydraulic fracturing in a weak rock, due to high shear stress concentration around the fracture tip, the rock will yield. And these plastic zones are very important because the energy is dissipated in these zones, and we need much higher pressure to propagate the fracture. And we can see what that means later in terms of the effective fracture toughness, the apparent fracture toughness. To investigate that, as I say, we set up elastoplastic, fully coupled hydraulic fracturing model. We took into account all the processes in a coupled manner, the fluid flow in the fracture, the rock deformation for weak rocks, using plasticity theory and Mohr-Coulomb. And we use also a good, robust fracture propagation criterion based on the cohesive model. On the cohesive model, basically this model expresses the stress which is carried in the area perpendicular to propagation as a function of the separation. And then the stress as increases near the fracture tip cannot go higher than the tensile strength of the rock, and then we follow a kind of a softening behavior until complete separation. And around this process zone, where we try to model through this cohesive model, the process zone, there is a lot of detailed work done also by Joeseph Labuz in this department. In the past and more recently, I saw some work. And finite element analysis. And in this picture, you can see the profiles of a propagating elastoplastic fracture. Starting from here, you just see a quarter of the profile as the fracture propagates. There is a quarter below, and the symmetry image on the other side, just ignoring the wellbore geometry. So as the fracture propagates, starts from here and it propagates. And now some of the results, we found that the plastic fractures are wider, and of course if they are wider, for the same pumping time will be shorter. So shorter and wider than what elasticity predicts. Then if we look at the pressure profile in the fracture, so this is here we have a fracture of 2.5 meters long, and this is the pressure profile as the fracture propagates. And the red, it's the solution of elasticity, the blue with plasticity. You can see here actually the fluid lag with plasticity, it's much smaller than elasticity. We have larger fluid lag with elasticity. And as a result, you can see back at the wellbore here, there is not a big difference between plasticity and elasticity for the same fracture length. Of course, there is to say that as the fracture propagates, the pressures predicted by elasticity, it's the red one. With plasticity, it's higher. But because the created fractures have different volumes, if you look at pressure versus time, what we measure in the field, we find that with plasticity, it's much higher the pressures than what elasticity predicts. And the other thing also with plasticity, as the fracture grows, we have increase in the pressure for some steps until we reach this point. Until at this point, the plastic zones are fully developed. They grow, they are fully developed, and after they are fully developed, the pressure drops, as you can see here. The other thing which it's very important result also, we calculate the effective fracture toughness due to this plasticity. And we use one of the energy criteria, the J integral. Basically, we propagated the fracture with a cohesive model, but at the same time, we took contours of J integral, and it was possible to calculate this increase in the apparent toughness. And with elasticity, of course, it's constant, doesn't increases the toughness during propagation. With plasticity, you can see that it increases with the first propagation steps, and then it reaches a kind of asymptotic value. Here in this case, from 1, we reach a limit value around 9 megapascal square meter. We did calculation, and we calculate apparent toughness up to more than 30 megapascal square meters. And of course, how important is plasticity? It depends on the size of the plastic zones. And we try to do some scaling, looking into some characteristics length. And apparently, we expect that this characteristic length, which defines the size of plasticity, should be proportional to the deviator of the in situ stresses. Will depend also on the rock parameters like toughness and tensile strength. And there is another characteristic length which was produced by a solution we worked in Schlumberger Cambridge Research when Emmanuel was there. And then it was investigated further, which basically that this plastic zone will depend also on the Young's modulus, the plane strain Young's modulus, the pumping parameters, viscosity and flow rates, and the compressive strength of the rock. And then we try to show these results in numbers, taking again a vertical fracture which can propagate vertically or horizontally, and we calculate values of the effective fracture toughness. And I can keep in cost the same values, keeping the same values for some parameters. In this case, we varied the rock strength as we moved horizontally like that. Strong rocks here, weak rocks here. And then the stress field, isotropic stress field here in this row, and highly anisotropic stress field in the last field. So you can see here when you have weak rocks and highly anisotropic stress field, when we propagate vertically, then we have high value of the apparent toughness. And in this case here, what we show the sensitivity of this, the increase in the apparent toughness with the pumping parameters. Again, pumping parameters, when we moved horizontally here, we have high viscosity or high pumping rates is the ratio in this column here. And with in each row, we go to highly anisotropic stress field. Highly anisotropic stress field and high pumping parameters, high value of pumping parameters, gives again a high value of the effective fracture toughness. Just to show some experimental results on fracture toughness, how it varies with confining pressure. I found this paper, Funatsu, it's from Japan, published in 2004, and basically they show that the fracture toughness increases with the confining pressure, in this case by 5 times, but as you can see here, we haven't reached a limit value yet. If it was possible to continue, it will increase even further. Just how the fracture toughness varies with the confining stress. And even under isotropic stress field, probably this increase will be higher with anisotropic under anisotropic stresses. The other thing I looked at was the fracture closure, okay? How the fracture closes when it's created in a weak rock, which yields, okay? And then after the fracture reach this profile here, 8 meters long, we allow the fracture to close and look at the pattern that the fracture closes. The theory of elasticity predicts that the fracture closes uniformly across its length and may contact the two faces when the pressure drops to the value of the EC2 stresses. And this is the way they calculate the closure stress for calibration, the big hydraulic fracturing operations after that. In this case, with plasticity, we see that the fracture closes initially everywhere, just from the relief of the stresses in the process zone, and then it closes first near the fracture tip, as you can see from here, and last near the wellbore. And if we look at the pressure versus time, this is during propagation, and then during closure, we allow it to close after we reach this value here. It drops rapidly, and then it will close here in negative net pressures. And also the same pattern when we reach longer fracture, again, in the same area here. Which means that if we take that, the fracture is closed for this value here, we'll underestimate the closure stress. And as a result, we'll have discrepancy later when we design the large hydraulic fracturing operations. And to show this, also in some of the experiments, these experiments were run in Delft University. There was a consortium supported by Schlumberger and other companies at that time. It's just the big blocks, hydraulic fracturing, fully monitoring. And then they look at the fracture geometry and the pressures from the experiments. In the case of the strong rock, you can assume here that it behaves elastically. In the case of the weak plaster, it behaves plastically, let's say the weak plaster, weak rock. In the case of the strong rock, the red line shows the fracture closure, the width of the fracture closure, which follows this pattern here. Someone can assume that the fracture has closed here. And if we take the pressure for this value here, we can see that the pressure is quite close to the confining stress, to the closure stress. So in that case, it will work quite well. If we go to the weak rock, weak plaster, the pattern of the fracture closures, the width, it goes like that. And one wear will take closure here, that the fracture has closed here. And the corresponding pressure to this value here, it's this one, which much below that the confining stress, okay? And this is a very important result because it's always the discussion we had, and with Emmanuel, okay, plasticity, it's important for short rock, for short fractures, which we understand, because if the fracture gets very long, the size of plasticity relative to the fracture length, it's not important. But these operations for the calibration of hydraulic fracturing is carried out in short rocks, in short fractures. So we create a fracture of 2 to 3 meters long, and then we allow it to fracture to calibrate the operations. We change also the stresses after fracturing in weak rocks. We do hydraulic fracturing. We allow the fracture to close on the proband. Proband is the material, like sand, who is keeping the fractures open. And after we allow it to close, we have all the stress redistribution. And the other thing we found that after the fracture has closed on the proband, it's much stable of deformation. Before fracturing, you can see actually this in this diagram here, which I call it yield factor. And the fracture is here, and this is a line perpendicular to the fracture face, okay? If you go far away, it's like not having any fracture. And here we selected the parameters to be very close to the yielding. After we did the fracturing and we look at this yield factor, we found that we push it away from the failure line. So the formation is more stable, and it will not fail to produce sand for the frac packs applications which I mentioned. And we extended this, the results I presented before were for dry rocks, okay? Then we extended the results in elastoplastic rocks. Basically, we modeled also the leak off of the fracture fluid from the formation and the diffusion of the fluids and the pore pressure in this modeling. And we use actually we used Abacus for this modeling, okay, Abacus. Used by one of my PhD students to do this calculation. We thought to go to Abacus because it has better solvers, better interfaces, geometry, but it had also the limitation. With Abacus, for example, we couldn't model the fluid lag. And the other thing also, that was the cohesive model, again, type of thing. We did also some sensitivity analysis on how the results depend on this cohesive model. And we found that the loading path, as we call it, the elastic path, affects the results, actually affects the development of the process zones, the loading path. The exact shape after the peak, which expresses the damage of the rock, the splitting of the rock, the exact shape doesn't affect much the results. But the loading part, it affects a lot the process zone and the results. And some quick comparisons. The fracture opening versus time with elasticity, poroelasticity, and poroplasticity. And here actually what we found is porosity interacts with the process zone. That's the reason the fractures are wider. Some will expect narrower fracture due to the back stresses. And the poroelastoplastic, it's of course much wider. And some results for the pressure versus time. Again, higher pressures for the poroelastoplastic case you can see here. Now, another thing I tried to think also that what is the role of dilation? The results I showed before was for associative plasticity. Dilation equals with friction, and try to see what will be the role of dilation. And just to tell you that the non-associative case, it's in between the elastic case and the associative case, the solution. It's in between. And we can show that also if we look at the stress concentration around the fracture tip. If we know for elastic material, we have the square root singularity 1/2 for the elastic materials, okay? Now, if we go to plastic materials and we can express the effective plastic strain as a function of effective stress in this power law form, then we will have a singularity of this form, R to the minus S, and we have this well-known singularity in the fracture mechanics community. HRR is called Hutchison, Rice, and Rosengren, which is S1 divided by N plus 1, which is basically it's weaker than the elastic singularity, okay? It's weaker than the elastic singularity. For non-associative plastic material, we show in this work with David Durban from Technion, Israel, we show that the singularity, it's even weaker than the HRR. It is given by this form here. It's even weaker. and this, the mu minus eta, expresses the level of the non-associativity, okay? The level of non-associativity. So basically, the non-associative case is in between elastic and associative case. And we show that also with finite elements calculations. Now, we did also some analytical work. Analytical work, it's always useful to identify the critical parameters, especially the combination of the critical parameters. In this simple model, relative simple model, we have again the fracture here and the plastic zones around the fracture tip as the orange shape I shown before. We say that we will replace these plastic zones with a pair of dislocations, we say it. The distributed plasticity will replaced by this pair of the superdislocation. This is what we called, again borrowing from work in metals, and I did this work with Colin Atkinson. And we will determine this, the unknown. In this case, the unknown will be the position where this superdislocation will be, the strength of the dislocation. That will be the major unknowns. And basically, what equation and condition we used, if I start with the net pressure again is the definition of the pressure in the fracture minus the closure stress, minus this stress, which is connected the net pressure with the stress intensity factor for an elastic material. For a uniformly loaded fracture, the length of the fracture is 2 alpha, as you can see here. And the position of the dislocation is expressed by this number, this parameter here. And the condition we use is that the stress intensity factor at the fracture tip, due to the loading and due to the contribution from the dislocation, should be equal with the fracture toughness of the rock. The stresses at the superdislocation should satisfy Mohr-Coulomb, the yield criterion, and also that the crack will act in such a way to maximize the crack opening displacement. And this condition was possible to give us the theta, this inclination of the superdislocation. Now, for small scale yielding, when the size of the plastic zone are much smaller than the size of the fracture, the length of the fracture, and for fracture toughness equals 0, it was possible to find this unknown in dimensionless form here, the position of the dislocation L, the strength of the dislocation B, the crack opening displacement, and the force of the dislocation, which is an indication of the strain energy which is needed to create the fracture, this force here. And then I will show some of the results based on different parameters of these unknowns here in dimensionless form. And basically, if we look at frictionless or undrained analysis, friction 0, and we look at these unknowns I said before, the value of this unknown in dimensionless form in the vertical axis as a function of the stress field. And you can see here that when we are in isotropic stress field, it's easier to create and propagate a fracture. We need more energy if we look at the force, this blue line, for example, this line here, a peak line. We need much energy to propagate the fracture as the field is becoming non-isotropic, and beyond the value, it will not be possible to create a mode 1 fracture. And this solution for small scale yielding and large scale yielding. Similar results when we have a cohesive frictional material. Now the critical parameters is this one here, okay? Because I will use this parameter here as the brittleness index later. So Again, isotropic will be close to this area. And this is more likely corresponds to the case that we propagate the fracture horizontally. It's not exactly on the zero line. It's not fully isotropic, the stress field, because we have the third stress as well. So we are around this area, let's say. And then we go to anisotropic stress field to propagate vertically. Again, we are in this area, so we need more energy to propagate the fractures, to create vertical fractures. And if we look at this diagram, we say that the values of 0 to 1 correspond to fracture propagation of increasing ductility from brittle to small scale to large scale, and to 1, and which one will correspond to the case that we require infinite energy release for unit advance. And again, I introduced this parameter here, which was basically was this one. I just took 1 minus that parameter to be consistent with some other brittleness parameters which were proposed in the literature. We say that we need a brittleness index to use as a candidate selection for intervals to do hydraulic fracturing in shale reservoirs, okay? We talk about brittleness, okay, and ductility. So most of these parameters actually were based on stress-strain curve, which is the ratio of the elastic strain over the total strain, or the elastic energy over the total, compressive strength minus tensile strength, different proposal, the friction angle. And in this definition, which people in the oil industry, they like it because it's based on dynamic measurements. In the field, actually, they do dynamic measurement, wave propagation, seismic wave propagation, or sonic wave propagations. So if we know the dynamic modulus, then you can do correlations to propose to get a brittleness number. This was one of the formulas was proposed, which has some problems because this formula doesn't predict that the brittleness should decrease with confining stress. We expect that confining stress will decrease the brittleness and decrease ductility. This doesn't follow the right tendency. And from the work I presented, it's clear to me that what is brittle? Brittleness cannot be used in isolation of material parameter. It's a combination also with the stresses of the confining stress. We know very well that confining stress increases the ductility. So an index should be a combination of the stress regime and the material parameters. And okay, I think I'm doing okay with the time. Now, we tried also to do some simple calculations, looking into for the CO2 geological storage again, and what it will happen to the results I presented before if the material parameters are damaged by the corrosive action of the CO2. CO2 is corrosive. So we try to decrease these material parameters to the extreme degree by 10 times. I say that the cohesion will be decreased by 10 times. And the fracture toughness will be decreased by 10 times. Actually, this is a very extreme degree because there are some experiments. There are experiments run in different places. They show some decrease in the material parameters, but not to this degree. Anyway, it doesn't cost here. It's calculation. I say I will repeat the calculations for decreasing both the fracture toughness of the rock and the cohesion to the extreme value. And after we did the comparisons again, we found that for the damaged material, it's even more difficult to propagate a fracture because we decrease the fracture toughness, but at the same time decreases the cohesion as well, so we get more plasticity. We get more apparent fracture toughness, as I showed before, more effective fracture toughness. And of course, in the oil industry, when you made these discussions that the fracture will propagate horizontally and not vertically, they say, they look very strange to this suggestion. We know they say that if we propagate vertically, the closure stress decreases. So the fracture should go vertically and not horizontally. Horizontally, the closure stress doesn't change. And I tried to write down some simple equations to see the comparison, okay? So the net pressure is in definition again. Pressure in the fracture minus the closure stress. Linear elastic fracture mechanics, uniformly loaded fracture. We have the stress intensity factor given by the net pressure times square root of the fracture length, half fracture length, given by this, and the fracture will propagate when we reach the K, the fracture toughness of the rock. When this parameter reaches this value, the fracture will propagate. We can solve this equation for the pressure in the fracture, which is equal to the closure stress, minimum issue stress, plus the fracture toughness divided by the square root of the fracture length. So the pressure in the fracture must exceed the closure stress and also this guy. Now, if you look at how the closure stress, this guy, changes as we are moving vertically, we can use the stress gradient, which is around 0.7 psi per foot, okay? Which means 50.8 kilopascal square meter per meter. This is the stress gradient as we are moving vertically for the minimum stress. Now, so as the fracture propagates vertically upward, the resistor decreases by this guy here, but may increase proportionally to this guy here due to the effective fracture toughness, which is of the order of megapascal, 1,000 meters long, okay? Of course, if the fracture becomes very long, this guy will be diminished, but we need very, very long fracture, 10 to the 6 meters before we have this term to dominate over that. So this, I try to make the point that the fracture is more likely to propagate horizontally. And I reached the conclusion just quickly to say plasticity plays a shielding mechanism around the tip, resulting in a significant increase of the apparent or effective fracture toughness, as we call it, results in higher pressure and larger width everywhere. Even dilatancy tends to close the fracture tip. Closure pressure in plastic rock may be significantly lower than the far field stress on the fracture plane, and this will underestimate the closure stress in the calibration, which I said before. We have stress redistribution and more stable formation after fracturing. This was the introduction of this brittleness index, which I was introduced for selecting intervals to do hydraulic fracturing. And the CO2 related application, more likely that the fracture will propagate horizontally than vertically. And if the fracture propagates vertically, we'll have some benefits to increase the ejectivity and storage capacity. And of course, if CO2 damage both cohesion and fracture toughness, proportionally, then we need higher energy to propagate mode 1 fracture. Mode 1 fracture. We still, mode 2 or mixed mode is still under investigation. And definitely it's not the full story here. We need more work to look at this issue. This is just first suggestions. Okay. Now we organized next summer in May, actually, in Cyprus, the international workshop on bifurcation and degradation in geomaterials with Joeseph Labuz in Cyprus. And this was one of the major topics of and the contribution of Ioannis Vardoulakis. We just mentioned that. There is a continuation of that. And many of the students actually, after me and Joeseph Labuz, younger students are quite active nowadays in different universities around the world. And it was very nice to see that, okay? And they are very active in this area. I think I have this, and one of the last pictures of Ioannis Vardoulakis from this project they had on landsliding in his last years. Okay. Thank you very much.
Thank you, Panos. We have time for a few questions or comments.
Thank you, Panos, for your lecture. There's something which puzzles me a little bit. Some of your calculations suggest that this effective toughness asymptote. So that suggests that the size of the plastic zone becomes asymptote.
Yeah.
So the bigger question is that what scales the size of those plastic zones? Because if you have let's take the limiting case where toughness equal to 0, then the only length scale will come from the injection. The material has no length scale. The viscosity has no length. The fluid has no length scale. So I mean, so something that I have not put my head around a long time, but I'm wondering, does the plastic zone increase with the size of the fracture, or does the plastic zone comes to a constant length dimension? If you see what I mean.
So
do you have
say
any insight on that? No, I'm just.
So basically, if you do this without cohesion, fracture is sand, for example.
Yeah,
but
there's not very little toughness. No, let's say that toughness equal to 0. Then there's no length in that material.
Toughness, but then we talk about apparent toughness.
You know, in a sense, so you have this plastic zone. So my question is that what scales the size of the plastic zone? What scales the toughness? Does it comes to a constant value, or does it keep increasing? So if you imagine the fracture,
I think it tends to a limit value. This is what I believe. Now, where that will be the limit value, we did calculations for very weak rocks, and we show that increasing the apparent toughness by 30 times, 30 megapascal square meters. And it was still, we could see the tendency to reach asymptotic value, even for that high value. Yeah. So, but of course, once it's fully developed, then as the fracture becomes longer, it will become less important, definitely. But this is what I mentioned. We look at weak rocks, applications for short fractures, like for sand control, calibration test, mini-frac, short fractures, and the confining pressure. I mean, the confining pressure down the high stresses will push for more ductile material.
Okay, if there are any other additional questions or comments, I'd like to take this time to recognize Panos as the 2016 Vardoulakis Lecturer with this certificate of achievement. So once again, Panos, thank you very much.
Oh, thank you very much. Thank you. Thank you, John.
We have to take a picture after.
Okay, thank you.
Thank you.
Very nice.